Chemistry of a Menace was produced at Canisius College, Buffalo, New York, under a grant from the Niagara Frontier Section and the sections of the Northeast region of the National Association of Corrosion Engineers. It was prepared under the guidance of Drs. Frank Denham and Joseph Biron by Teresa Amabile, a senior chemistry major at Canisius College, Diane Cookfair, a senior at Kenmore East High School, and Michael Shanks, a senior at Maryville High School. Corrosion, the Chemistry of a Menace, is presented to alert high school students to the possibility of corrosion control as a career field.
I didn't even know places like this existed.
And this plant was operating just 12 years ago.
How did things get so bad anyway?
This specimen's in such bad shape, I'm going to have trouble even handling it.
You mean for your project on corrosion?
Uh-huh.
It's a little scary how quickly it happened. 12 years ago, that was a busy plant.
Well, corrosion is a very common problem. I never really paid any attention to it before I started gathering specimens for this project. But going home today, just look around you. It's literally everywhere. Almost anything made out of iron will corrode when exposed to moisture and air, anything from a ship in the harbor to your brother's swing set. In fact, it's so common that 20% of the iron produced per year goes to replace iron corroded away.
But if it's so common and so expensive, why doesn't someone just stop it?
It's not that simple. Corrosion occurs almost anywhere there's moisture. The more moisture, the more likely it is to form. I set up this demonstration just before you came to show the conditions necessary for corrosion. I prepared a solution of cupric chloride in one beaker, an equally concentrated aluminum nitrate solution in the other, and suspended a strip of tin in each. Let's take a look at them. It's only been 5 minutes, and already the tin from the copper chloride solution shows heavy corrosion. However, the tin strip placed in the solution of aluminum nitrate shows no reaction.
Why did corrosion happen in the first solution and not in the second?
To answer that, we have to look at the Electromotive series. This series is a table showing the elements in order of reactivity, the most active being lithium at the top of the series. Here's an example of a very reactive metal, sodium. Since it is found so far above hydrogen on the chart, it corrodes very quickly in the presence of the water molecule. Now find tin on the chart. It's below aluminum but above copper. That's why tin corroded in the copper solution but not in the aluminum solution. A metal can only corrode in the presence of one which is less reactive than itself. In the copper chloride solution, the tin is replacing copper. Tin starts with a charge of 0, loses 2 electrons, and ends up with a charge of +2. These 2 electrons are taken on by copper, which goes from a charge of +2 to 0. The copper is reduced, that is, it gains electrons, and the tin is oxidized, it loses electrons. The reduction reaction is a copper ion plus 2 electrons yields an atom of copper metal, and the oxidation reaction, an atom of tin metal minus 2 electrons yields a tin plus 2 ion.
Well, I didn't see any copper chloride floating around rusting that old factory we found. What does all this have to do with that?
Maybe this will help you understand the correlation. It's a galvanic cell I set up a few days ago, and it works by the same process as corrosion, but here it's used to create an electric current. I placed a zinc strip in a solution of a zinc salt and a copper strip in a copper salt. The salt bridge allows slow passage of ions, a wire completes the circuit, and the voltmeter indicates electron flow. Zinc has a greater tendency than copper to give up electrons, so electrons released at the zinc flow to the copper through the conductor. This means that the zinc is called the anode, or positive electrode. Here, zinc atoms are oxidized. They give off electrons and form ions. The electrons flow through the conductor to the copper electrode. The copper cathode is negative because of its excess of electrons. Here, copper ions take on electrons to form copper atoms. In other words, they're reduced.
But I don't see any little wire connecting the different parts of that rusty car across the street.
Maybe the anode is just the place where corrosion happens, and the cathode is the part of metal right next to it. So it's really like a galvanic cell, but without the wire connection. Kind of like a short circuit. Well, what makes one section of metal become the part that corrodes in the first place?
Oh, many things. A small impurity, a scratch, a slightly different environment. Any of these could differentiate two sections even though they're right next to each other. In a rusting piece of metal, there are lots of little anodes and cathodes all over, so small you can't even see where they are. For the corrosion of iron in the presence of an electrolyte, the iron is oxidized according to this half reaction. This happens at the mini-anode area. At the same time, oxygen molecules dissolved in the water are being reduced at the mini-cathode like this. Oxygen plus water plus 2 moles of electrons yields hydroxide ions.
Oh, I see. If you add those two equations and then let that product react with oxygen and water, you get rust.
Fe, OH, taken twice, a solid, plus oxygen, a gas, plus water, yield Fe, OH, taken 3 times, a solid.
Now add all the steps together for the overall reaction. You can see the importance of both moisture and air to the rusting process. The final product will be the loose, flaky, reddish-brown substance we call rust.
I guess I knew that's what causes rust, but I'd never seen it before in equation form.
You said before that electrolytes are necessary for iron to corrode. I've forgotten what electrolytes are.
An electrolyte is a substance whose water solution conducts an electric current. Common electrolytes are acids, bases, and salts. In the case of a rusty ocean liner, the seawater contains salt, which acts as the electrolyte.
Is that why salted roads are bad for cars?
Yes, the salt that's used on roads in the winter to melt the ice serves as a very good electrolyte and helps to accelerate corrosion. Another thing that causes a lot of corrosion on cars is mud. That's because mud often contains salt, and the piece of metal under the mud is getting less oxygen than the metal around it.
Why would that cause it to corrode?
If you remember back to our discussion on the corrosion of iron, you'll recall that oxygen is reduced at the cathode. So the area with high oxygen concentration becomes the cathode, and the oxygen-shielded part under the mud becomes the anode and rusts. Rusting is especially costly to the motorist. There, do you see that car outside? That motorist has a real problem. It looks like he's got almost every conceivable rust problem. Let's go out and take a look at it. You can see that these paint blisters leave small areas open for corrosive attack. This means water and salt can get in, and since this spot is more open to oxygen, the metal around it under the paint will rust. There are many bolts and crevices around the headlight assembly to collect moisture and cause oxygen shielding. A number of areas of the car are involved in this problem, such as the joints connecting the bumper to the car body and the taillight cavities. Water collects between the floorboards and the mats and rusts areas near the door. And the wheels kick water up into the fender supports. In fact, any area that isn't uniform, like that crumpled fender, is a trouble spot.
What can you do to keep cars from corroding?
Well, first of all, you can dry your car after it's gotten wet, or at least leave it out in the open to dry rather than in an unventilated garage. This will keep the dampness out of the motor and other hidden areas of your car that are especially prone to rust. And many drivers are careless about opening their door into someone else's car. If your car is scratched with a parker's nick, get the scratch painted as soon as possible. Otherwise, rust may begin under the paint surface. Paint is a mixture of many different things. It includes a binding medium, that is, any substance which will stick to the metal surface as a thin film and prevent corrosion. Natural oils are often used in paint to protect the metal from direct contact with water and oxygen. Many auto paints also contain metals, such as zinc, whose oxides provide a protective film. Corroded trim also used to be a big problem, but new trim is stainless steel with an aluminum core. When corrosion starts, the aluminum corrodes and leaves the visible part rust-free. This method of protection uses what are called sacrificial metals. Zinc, aluminum, and magnesium are used to protect iron because they're more active than iron is. When placed next to it, they will become the anode and corrode rather than the iron. Here's a demonstration I set up several days ago to show the action of sacrificial metals. In a liter beaker, I placed some soil and saturated it with water. For the sake of accelerating the corrosion, I added some salt. Next, a strip of magnesium and an iron nail were connected by a conductor and both were inserted into the soil. Here's what happened. The more active magnesium became the anode and corroded preferentially to the iron. This method is used to protect underground pipelines.
Is there more than one kind of corrosion?
Yes, there are many different types. The simplest to talk about is uniform attack, where there's an even depth of corrosion over the metal surface. Then there's cracking, which is due to the joint action of corrosion and mechanical stress.
I visited Arizona last year, and I didn't see anything like this. How come?
Well, first let's review the conditions necessary for corrosion. Of course, moisture, oxygen, and an electrolyte are necessary. Also, the metal corroding must be more reactive than the element it's replacing in solution. Finally, the area with lower oxygen concentration will become the anode, while that with more oxygen won't rust at all. Recent studies reveal that pollution also has a serious effect on corrosion. One study showed that an industrial community has 17 times as much rust-producing fallout as one of identical size without heavy industry. When chemical waste is dumped into lakes and rivers, they become much better electrolytes because of the acids, bases, and salts in industrial wastes. Also, sulfur oxides in the air form sulfuric acid in the presence of water vapor. Let's take a look at a map which shows where all these conditions are worst in the United States. The degree of corrosion depends mainly upon the humidity and pollution levels in an area. Therefore, the coasts and areas around the Great Lakes are prone to the most severe corrosion. Along the southeastern coastal cities, such as Norfolk, Charleston, and Miami, the corrosion is bad because of high humidity. The northeastern coastal region, including New York City and Boston, are problem areas because of high humidity and industrial fallout. The next most corrosive area is immediately adjacent to the coasts. Cities such as Seattle, Portland, and Washington, D.C., and the large section between the Great Lakes region and the southern coast. Here there is high humidity and industrial fallout. Corrosion is more mild in the areas adjacent to the ones just mentioned, and western states like Utah, Arizona, and New Mexico are most free of corrosion because the air is very dry and there's no great industrial fallout problem. But corrosion is still very serious almost anywhere you go. Throughout the world, corrosion engineers devote all their research to this problem and its solution.
You've mentioned a couple methods of protection from corrosion. Are there any others?
There is one important method of protection I haven't mentioned. Some metals are protected just by the nature of their corrosion products. For instance, a piece of aluminum can be polished so much that it may be used as a mirror, like the one in that restaurant across the street. Within just a few days, it will be covered with a whitish film. This is its corrosion product, an oxide, but once it forms, it protects against further corrosion. Unfortunately, the most common metal in use offers no such self-protection.
If I ever thought of corrosion before, it was something common and unimportant. I never realized it could be so drastic.
Active corrosion is taking place in working facilities as well as in those that are shut down. The discipline of corrosion control is infinitely more complex than has been shown in this film. The control of corrosion through the proper use of materials, coatings, inhibitors, or cathodic protection is very successful, and through education and scientific investigation, progress will continue to be made in this challenging field.